Right now, something extraordinary is happening. 126 million miles away from Earth, a visitor from another star system is screaming toward our sun at speeds that would make a fighter jet look like it's standing still. In just 18 days, hours and minutes, Comet 3I at LS will reach its closest approach to our solar furnace, and what happens next will rewrite everything we thought we knew about these ancient wanderers from the void. Picture this: you're standing on the surface of this interstellar traveler, watching the sun grow larger and more menacing with each passing moment. The temperature around you is climbing from the bone-chilling cold of deep space towards something that would vaporize metal in seconds. Behind you stretches a trail of glowing gas and dust, evidence of your world literally boiling away under the increasing solar assault. This isn't science fiction. This is happening right now, and the countdown has already begun. T-18 days. The comet's hyperbolic trajectory is unlike anything born in our solar system. While our familiar comets follow predictable elliptical paths, returning every few decades or centuries like clockwork, 3I at LS follows a path that screams of alien origins. Its trajectory bends through space like a slingshot, gaining speed with every mile it travels closer to our star. At 130,000 miles per hour, it's moving faster than any human-made object has ever traveled. To put that in perspective, if you could somehow catch a ride on this cosmic bullet, you could travel from New York to Los Angeles in less than 90 seconds. But speed is just the beginning of this story. What makes 3I Atchels truly remarkable isn't just how fast it's moving, but where it came from and what it's carrying with it. This isn't debris from our solar system's formation 4.6 billion years ago. This is a time capsule from another star, another world, carrying secrets that predate our sun itself. And in 18 days, that time capsule is going to be torn open by forces so intense. They'll strip away layers of ancient ice that have remained frozen since before Earth existed. The mathematics of this encounter are staggering. Every hour that passes, 3I at LS covers a distance equivalent to traveling around Earth's equator more than 5 times. Every minute, it races across 2,167 miles of space. Every second, it devours 36 miles of the void between it and our sun. This isn't the gentle drift of celestial mechanics we're used to thinking about when we imagine space. This is violence in slow motion, a cosmic collision course that's been building for millions of years. T-18 hours. By now, the comet is entering the realm where our sun's influence becomes overwhelming. The solar wind, that constant stream of charged particles flowing outward from our star, begins to interact with the comet's growing atmosphere in ways that create an electric crackle across its surface. Imagine standing in a lightning storm where every bolt carries the energy of a nuclear weapon, and you begin to understand the environment. 3I at LS is entering. The surface temperature is climbing past the point where water ice can remain stable. What was once a frozen world, darker than charcoal and colder than Antarctica's worst winter, is beginning to transform. Sublimation, the process where ice turns directly to gas without melting, starts in earnest. Water molecules that have been locked in place since the comet formed are suddenly free, expanding and accelerating away from the surface at thousands of miles per hour. But here's where the story takes its first unexpected turn. Most comets don't start showing significant activity until they're much closer to the sun, typically inside the orbit of Mars. Yet 3I at LS began releasing water vapor when it was still nearly 3 times farther from the sun than Earth is. This shouldn't be happening according to everything we know about cometary physics, and it's the first clue that we're dealing with something extraordinary. T-18 minutes. The comet is now racing through space at a velocity that defies human comprehension. To give you a sense of scale, if you could fire a bullet from the most powerful rifle on Earth, 3I at LS is moving more than 300 times faster than that bullet. It's moving so fast that if it were traveling toward Earth instead of the sun, we would have less than an hour of warning before impact, even if we spotted it from the distance of the moon. The surface is now experiencing temperatures that would instantly vaporize any Earth-based material. The pristine ices that have been the comet's signature for eons are boiling away in torrents, creating jets of superheated gas that stream behind the comet, like the exhaust from some impossible engine. These aren't gentle puffs of vapor. These are explosive outbursts carrying thousands of tons of material into space every hour. What's remarkable is that we can see this happening from Earth. Through our most powerful telescopes, 3I at LS, appears as a fuzzy star with a growing tail that stretches across millions of miles of space. But what we're seeing is just the visible light scattered by dust particles. The real action, the water vapor and other gases streaming away from the surface, requires specialized instruments to detect. And those instruments have been revealing secrets that challenge our fundamental understanding of how comets work. The electromagnetic spectrum tells a story that visible light alone could never reveal. In infrared wavelengths, we can see the heat signature of the comet's nucleus, watching in real time as different regions warm and cool as it rotates. In ultraviolet light, we can detect the hydroxyl molecules created when water vapor is broken apart by solar radiation. In radio wavelengths, we can hear the whisper of organic molecules that might hold clues to the chemistry of life itself. But there's something else happening, something that has scientists around the world staying up late, double-checking their calculations, and questioning assumptions they've held for decades. Mars Express, one of the European Space Agency's most successful interplanetary missions, captured something during its routine observations that nobody expected to see. The data is still being analyzed, but preliminary reports suggest that 3I at LS isn't behaving like any comet we've ever encountered. The orbital mechanics alone tell a story of incredible precision and cosmic timing. For this interstellar visitor to arrive at our solar system at exactly the right angle, at exactly the right speed, to achieve this close approach to the Sun, requires a chain of gravitational influences stretching back millions of years. The tiniest variation in its original trajectory, a difference measured in fractions of degrees, would have sent it careening past our solar system entirely, invisible and undetected. Instead, we're witnessing what might be the astronomical equivalent of a hole-in-one from another galaxy. The probability calculations make your head spin. The chances of an interstellar object achieving this kind of solar encounter are so small that some astronomers are wondering if we're missing something fundamental about how these objects move through the galaxy. As we count down these final moments before perihelion, the closest approach to the Sun, it's worth remembering that we are the first generation of humans to witness such an event, with the tools to truly understand what we're seeing. Our ancestors could only watch comets with naked eyes and wonder about their meaning. We can dissect their composition, track their movements with precision, and even predict their behavior decades into the future. Yet 3I at LS is teaching us humility. Despite all our technological prowess, despite our sophisticated models and powerful computers, this visitor from another star is showing us phenomena we can't fully explain. The water outgassing that began when the comet was still far from the Sun, the unusual composition detected in its tail, the unexpected brightness variations that suggest internal structure more complex than our simple models predict. T-0, perihelion approaches, and with it, the moment of maximum revelation. In the next few hours, as 3I at LS swings around our Sun at its point of closest approach, it will experience forces and temperatures that will fundamentally alter its structure. The outer layers, accumulated over millions of years of interstellar travel, will be stripped away like paint in a blowtorch. What emerges from this solar furnace will be different from what went in, changed, transformed. And in that transformation lies the key to understanding not just this single comet, but the nature of interstellar space itself, the formation of planetary systems beyond our own, and perhaps even the distribution of the basic ingredients for life throughout our galaxy. The flames are dancing now, invisible to our eyes, but measured by our instruments. The electric crackle of solar wind meets cometary atmosphere in a display of raw physics that would humble any earthly storm. And somewhere in the data streams flowing back to Earth, in the spectroscopic signatures and thermal measurements, lies evidence that will challenge everything we thought we knew about these wanderers from the stars. This is just the beginning of the story. What happens next will surprise even the scientists who have dedicated their careers to understanding these cosmic messengers. The moment has arrived. October 29th, 2025, and 3I at LS is skimming the edge of annihilation, passing within 126 million miles of our Sun at perihelion. To understand the violence of this encounter, imagine every piece of ice in your freezer suddenly exposed to the heat of a blast furnace. Now multiply that by the mass of a mountain, and you begin to grasp what's happening to this interstellar visitor as it races through the solar corona's outer reaches. At this distance, the Sun isn't just a source of light and warmth. It's a raging nuclear reactor whose influence extends far beyond what we can see. The solar wind, That constant stream of charged particles flowing outward at over 1,000,000 miles per hour slams into the comet's expanding atmosphere with the force of a hurricane made of plasma. Magnetic field lines, invisible to our eyes but absolutely real in their effects, wrap around the comet like electrical cables, carrying currents that would power entire cities. The surface temperature has now exceeded 400 degrees Fahrenheit, hot enough to melt lead, hot enough to instantly vaporize any water ice that reaches the surface. But this isn't happening gently. The transition from solid ice to superheated gas creates explosive jets that blast material into space with velocities reaching 2,000 miles per hour. These aren't the gentle puffs of steam you might see from a hot spring. These are volcanic eruptions of ice and dust, carving canyons and craters in the comet's surface in real time. What makes this encounter truly remarkable isn't just the drama of the moment, but what it's revealing about the fundamental nature of interstellar objects. Sarah Chen at Auburn University was the first to detect something that shouldn't exist: hydroxyl molecules streaming from 3I at LS when it was still 2.9 AU from the Sun, nearly 3 times farther than Earth's orbit. This discovery sent shockwaves through the astronomical community because it challenges everything we thought we knew about how comets work. Hydroxyl is the signature of water being torn apart by solar radiation. When water molecules absorb ultraviolet light from the Sun, they split into hydrogen and hydroxyl, creating a distinctive spectroscopic fingerprint that astronomers can detect from billions of miles away. But here's the problem. This process requires intense solar radiation to occur, and at 2.9 AU, that radiation should be far too weak to trigger significant water outgassing. Yet the data doesn't lie. Auburn's team detected hydroxyl emission equivalent to 40 kilograms of water being blasted into space every second, when 3I at LS was still in the outer solar system. To put that in perspective, that's like a fire hose blasting 10 gallons of water every second, except this water is expanding into the vacuum of space at thousands of miles per hour, and the hose is attached to a cosmic iceberg traveling at 130,000 miles per hour. The spectroscopic analysis reveals a composition unlike anything we've seen in solar system comets. Traditional comets are dirty snowballs, mixtures of water ice, dust, and various frozen gases like carbon monoxide and methane. But 3I at LS shows signatures of carbon dioxide-rich ice, atomic nickel in concentrations that shouldn't exist in normal cometary material, and organic compounds that suggest a formation environment radically different from our solar system's birth nebula. The carbon dioxide detection is particularly intriguing because CO₂-driven ice is more volatile than water ice. It sublimates at much lower temperatures, which might explain the early onset of activity. But the concentrations detected don't match theoretical models of cometary formation. It's as if this comet formed in an environment where carbon dioxide was far more abundant than in the disk of material that gave birth to our solar system. The atomic nickel signature is even more puzzling. Nickel is a heavy element, formed in the nuclear furnaces of massive stars and distributed through space when those stars explode as supernovae. Finding significant nickel in a comet suggests that 3I at LS formed from material that was enriched by stellar explosions in ways that our local stellar neighborhood never experienced. It's carrying the fingerprints of stellar death from another part of the galaxy. But perhaps most intriguing are the organic compounds detected in the comet's tail. These aren't simple hydrocarbons like methane or ethane. These are complex molecules containing carbon, hydrogen, oxygen, and nitrogen, arranged in patterns that, on Earth, we associate with the precursors to biological chemistry. Amino acids, the building blocks of proteins, nucleotide bases, the components of DNA and RNA, molecules that, under the right conditions, could serve as raw materials for life itself. The detection method is a masterpiece of 21st century astronomy. Light from the comet's tail is collected by telescopes around the world, then split into its component wavelengths using sophisticated spectrographs. Each molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint that can be identified with extraordinary precision. It's like analyzing the contents of a distant campfire by examining the color of its smoke, except the campfire is millions of miles away and traveling at unimaginable speed. The data pipeline that processes these observations is a marvel of international cooperation. Raw photons collected by telescopes in Chile, Hawaii, and the Canary Islands are converted to digital signals, transmitted via satellite to data centers around the world, and processed by algorithms that can identify molecular signatures in noise levels that would have been undetectable just a decade ago. The sensitivity is so extreme that astronomers can detect the presence of specific molecules even when they represent less than 1 part per billion of the comet's total composition. Yet for all our technological sophistication, the observations of 3I at LS are revealing phenomena that challenge our theoretical understanding: the early water outgassing, the unusual composition, the unexpected brightness variations that suggest internal structure more complex than simple models predict. Each new observation raises more questions than it answers. Dr. Martinez at the European Southern Observatory described the situation perfectly. It's like finding a geyser on Pluto. The physics says it shouldn't be happening, but there it is, captured in spectrum after spectrum, defying our models and demanding new explanations. The magnetic environment around the comet during perihelion is unlike anything in Earth's experience. The Sun's magnetic field lines, stretched and twisted by the solar wind, interact with the comet's ionized atmosphere to create electrical phenomena that would dwarf any terrestrial thunderstorm. Lightning bolts carrying millions of volts of electrical potential arc through the comet's tail, heating gas to temperatures of tens of thousands of degrees and creating auroral displays that would be visible across entire continents if they occurred in Earth's atmosphere. The gravitational forces acting on 3I at LS during perihelion are also extraordinary. The Sun's gravity at this distance creates tidal effects that stretch and compress the comet's nucleus, potentially triggering internal fractures that could lead to fragmentation. The differential heating between the sun-facing and space-facing sides of the comet creates thermal stresses that can crack rock and ice like glass in a fire. These extreme conditions are providing an unprecedented laboratory for studying the physics of cometary activity. Every jet, every brightness variation, every spectroscopic anomaly is a clue to understanding not just this individual object, but the entire population of interstellar comets that must be wandering through our galaxy. The data being collected during these crucial hours will be analyzed for years to come, revealing secrets about stellar formation, planetary system evolution, and the distribution of organic molecules throughout the cosmos. But even as scientists work to interpret the flood of data from perihelion, new mysteries are emerging. Ground-based observers are reporting unusual dust grain properties in the comet's tail, particles that reflect light in ways that suggest mineral compositions unlike anything seen in solar system objects. The implications are staggering. If confirmed, these observations would indicate that 3I at LS formed in a stellar environment with a fundamentally different chemical evolution than our own solar system experienced. The infrared observations are particularly revealing. At these wavelengths, astronomers can see the heat signature of the comet's nucleus directly, watching as different regions warm and cool as the comet rotates. The thermal maps show hotspots that correspond to active venting regions, where subsurface ice is being explosively converted to gas. But they also show cool regions that seem to be insulated from solar heating, suggesting an internal structure more complex than the simple rubble pile model typically applied to comets. The rotation period measurements add another layer of complexity to the story. As gas jets blast material asymmetrically from the comet's surface, they create a rocket effect that can alter the object's spin. Careful timing of brightness variations reveals that 3I at LS's rotation period is changing, accelerating by measurable amounts as the comet approaches perihelion. This isn't unusual in itself, but the magnitude of the change suggests mass loss rates and internal structure variations that challenge existing models. Perhaps most intriguingly, the gas production rates don't follow the expected inverse square relationship with solar distance. As a comet approaches the Sun, the increased solar heating should cause gas production to increase predictably. 4 times closer means 16 times more heating and correspondingly more gas production. But 3I at LS shows production rates that are both higher than expected at large distances and more variable than models predict. Something fundamental about its composition or structure is different from ordinary comets. The perihelion passage is also revealing details about the comet's internal structure through careful observation of how it responds to solar heating. The time delay between peak solar heating and peak gas production provides clues about thermal diffusion through the comet's interior. The spatial distribution of different gas species in the comet's atmosphere reveals information about the vertical layering of different ices within the nucleus. Each observation adds another piece to the puzzle of understanding what this interstellar visitor is made of and how it formed. As the critical hours of Perihelion passage unfold, 3I at LS is being transformed from the frozen relic it was during its millions of years of interstellar travel into something new and different. The outer layers, accumulated during its journey through the galaxy, are being stripped away to reveal more pristine material from its original formation. It's like archaeological excavation in reverse, where instead of carefully removing layers to reveal ancient secrets, the cosmic environment is doing the excavation for us with forces measured in megatons and temperatures measured in thousands of degrees. And hidden in the flood of data streaming back to Earth, from dozens of observatories and space missions, there lurks an anomaly that will soon challenge everything. Scientists thought they understood about this remarkable visitor from another star. In the basement of Auburn University's astronomy building, at 2:17 a.m. on a rain-soaked Tuesday in September, Dr. Sarah Chen stared at her computer screen in disbelief. The hydroxyl detection software had just processed another night's worth of observations from the 10-meter Keck telescope, and the numbers glowing on her monitor shouldn't exist. According to every cometary model developed over the past 50 years, what she was seeing was impossible. Yet there it was, spectrum after spectrum, showing water molecules being blasted from 3I at LS at a rate of 40 kilograms per second, when the comet was still 2.9 astronomical units from the Sun. To understand why this discovery sent shockwaves through the astronomical community, you need to grasp the physics of how comets work. Water ice, the primary component of most comets, requires specific conditions to sublimate directly from solid to gas. The process depends on solar heating, and that heating follows the inverse square law with brutal precision. At Earth's distance from the Sun, 1 square meter receives about 1,360 watts of solar energy. At Mars's distance, that drops to about 590 watts. At 2.9 AU, where 3I at LS was when Chen detected the massive water outgassing, the solar heating should be only about 160 watts per square meter. That's not enough energy to drive the explosive water production Chen was measuring, not even close. It's like trying to boil a pot of water with a birthday candle. The mathematics simply don't work unless something fundamental about 3I at LS is different from every comet we've ever studied. And that's exactly what Chen and her team were beginning to suspect. The hydroxyl detection itself represents a triumph of modern astronomical technology. When water molecules in the comet's atmosphere absorb ultraviolet photons from the Sun, they split apart, creating hydroxyl radicals that emit light at very specific wavelengths. These wavelengths are like molecular fingerprints, unique signatures that can be detected across billions of miles of space. But the process requires sophisticated spectrographs, capable of measuring light intensity to precisions of 1 part in 10 million. Chen's team was using the high-resolution Shell spectrometer on the Keck telescope, an instrument so sensitive it could detect the light from a single candle on the Moon. Even with this extraordinary sensitivity, the hydroxyl signal from 3I at LS was strong enough to be detected in exposures lasting just a few minutes. That strength is what made the discovery so shocking. Normal comets at that distance would require hours of integration time to detect any hydroxyl signal at all. The data reduction process is where the real detective work begins. Raw spectra from the telescope contain light from the comet, mixed with light from the Earth's atmosphere, scattered sunlight, and electronic noise from the detector. Separating the comet's actual spectrum from this contamination requires algorithms that can identify and subtract thousands of spectral lines from atmospheric water vapor, oxygen, and other molecules. It's like trying to hear a whispered conversation in a crowded restaurant while someone else is playing loud music. But Chen's team had developed new techniques for this separation, using machine learning algorithms trained on thousands of stellar spectra to identify and remove atmospheric contamination with unprecedented precision. When they applied these techniques to the 3I at LS observations, the hydroxyl signal emerged from the noise like a lighthouse beam cutting through fog. The signal was not only detectable, it was overwhelming. The team spent weeks double-checking their analysis. They reprocessed the raw data using different algorithms. They compared their results with hydroxyl detections from other comets observed under similar conditions. They even obtained new observations from different telescopes to confirm their measurements. Every test confirmed the same impossible result. 3I at LS was producing water vapor at rates that violated fundamental assumptions about cometary physics. The breakthrough came during a 3 a.m. coffee-fueled discussion between Chen and her graduate student Marcus Rodriguez. They were reviewing literature on sublimation rates for various ices when Rodriguez made a connection that would prove crucial. What if it's not water ice driving the activity? He asked. What if it's something else, something more volatile, that's dragging water along with it? The idea seemed far-fetched at first. Traditional comet models assume that water ice is the primary volatile component, with small amounts of carbon monoxide, carbon dioxide, and other gases mixed in. But what if 3I at LS had formed in an environment where the ratios were reversed? What if carbon dioxide or some other highly volatile ice was the dominant component, with water ice carried along as a minor constituent? Carbon dioxide ice sublimates at much lower temperatures than water ice. At 2.9 AU from the Sun, CO₂ ice would be actively sublimating, creating gas jets that could easily exceed the velocities needed to carry water molecules along. It would be like a fire hose of CO₂ gas blasting through deposits of water ice, entraining and accelerating the water molecules to the high velocities Chen was measuring. This hypothesis led to a frenzy of new observations. If CO₂ was driving the activity, it should be detectable in infrared spectra of the comet's atmosphere. The team obtained time on the Spitzer Space Telescope, which had the sensitivity to detect the characteristic 4.3 micron emission line of carbon dioxide in space environments. The observations required months of planning and weeks of careful data reduction, but the results were worth the wait. The carbon dioxide detection was unambiguous. Not only was CO₂ present in the comet's atmosphere, it was present in concentrations far higher than typical solar system comets. The CO₂ to water ratio in 3I at LS was nearly 10 times higher than in any previously studied comet. This wasn't just a quirk of composition, it was evidence of formation in a radically different environment. But the carbon dioxide discovery raised new questions even as it answered old ones. Where did all that CO₂ come from? In our solar system, carbon dioxide ice forms only in the coldest regions beyond the orbit of Neptune. Yet the isotopic ratios in the CO₂ from 3I at LS didn't match the signatures expected from Kuiper belt formation. The carbon and oxygen isotopes were slightly enriched in heavy isotopes, suggesting formation in a region with different stellar nucleosynthesis history than our local galactic neighborhood. The laboratory analysis of this data reads like a detective story written in the language of quantum mechanics. Each photon collected by the telescope carries information about the quantum energy levels of the atoms and molecules that emitted or absorbed it. By carefully measuring the wavelengths and intensities of thousands of spectral lines, astronomers can determine not just what molecules are present, but their temperatures, velocities, and even the magnetic field strengths in their environment. The water production rate calculations require understanding the relationship between hydroxyl detection and parent water molecules. When water molecules are broken apart by solar UV radiation, they don't all produce hydroxyl immediately. Some create hydrogen and oxygen atoms directly. Others undergo complex photochemical reactions that can delay hydroxyl production by hours or days. Converting hydroxyl observations to water production rates requires sophisticated models of cometary atmospheric chemistry that account for these complexities. Chen's team developed new Monte Carlo simulations to model the hydroxyl production process in 3I. These simulations track millions of individual water molecules through their interactions with solar photons, accounting for the three-dimensional structure of the comet's gas cloud and the varying intensity of solar radiation with distance from the nucleus. The computational requirements were enormous, requiring weeks of processing time on Auburn's supercomputing cluster. The results of these simulations confirmed what the raw observations suggested. 3I at LS was producing water vapor at rates that could only be explained by a dominant volatile species more active than water ice itself. The CO₂-driven model matched the observations remarkably well, but only if the comet's nucleus contained CO₂ concentrations that were unprecedented in solar system objects. Late-night debates in the Auburn astronomy department became legendary as the team wrestled with the implications of their discovery. If 3I at LS formed with such unusual composition, what did that say about the stellar environment where it originated? If CO₂ could drive such intense activity at large solar distances, were there other interstellar comets passing through our solar system undetected, because they appeared inactive when observed by traditional methods? The broader implications were staggering. Comets are thought to be relatively unchanged, samples of the material from which planetary systems form. If 3I at LS represented typical interstellar comet composition, it suggested that planetary formation in other stellar systems might follow very different chemical pathways than in our own solar system. The carbon dioxide enrichment might indicate formation around stars with different evolutionary histories, or in regions of the galaxy where supernovae had enriched the interstellar medium with heavy elements in different proportions. The team's findings also had implications for astrobiology. Carbon dioxide is a key ingredient in many of the chemical reactions that can lead to complex organic molecules. If interstellar comets were enriched in CO₂, they might be more effective at delivering carbon-based chemistry to planetary surfaces than previously thought. The intense activity driven by CO sublimation could also create conditions favorable for complex chemistry within the comet itself, potentially synthesizing organic molecules during the comet's journey through interstellar space. As news of the discovery spread through the astronomical community, other research groups began reanalyzing their own observations of 3I at LS. The European Southern Observatory reported detecting unusual spectral features in their high-resolution spectra that they had initially attributed to instrumental effects. NASA's Infrared Telescope facility found evidence of other volatile species, including methanol and formaldehyde, at concentrations that correlated with the CO₂ detection. But perhaps most intriguingly, the Arecibo radio telescope detected faint signals that might indicate the presence of even more complex molecules. The signals were at the edge of detectability, buried in noise and atmospheric interference, but they appeared to match the frequencies of amino acid precursors and other organic compounds that could represent the building blocks of biological chemistry. Each new detection added another piece to the puzzle, but the picture emerging was unlike anything astronomers had expected. 3I at LS wasn't just an ordinary comet from another star system. It was a time capsule from a stellar environment that had followed a fundamentally different evolutionary path than our own, carrying chemistry that might represent alternative pathways to the complex molecules necessary for life. The water outgassing mystery had been solved, but in solving it, Chen's team had uncovered evidence of cosmic processes and stellar environments that challenged fundamental assumptions about how planetary systems form and evolve. The fire hose of water vapor streaming from 3I at LS was just the visible symptom of something far more profound, proof that the universe is capable of creating chemistry and physics that we're only beginning to understand. And hidden in the spectroscopic data, waiting to be discovered, were signatures of other molecules that would soon reveal even more shocking secrets about this visitor from the stars. In the Mission Control Center at NASA's Goddard Space Flight Center, the atmosphere is electric with anticipation. Wall-mounted screens display orbital trajectories, instrument status readings, and countdown timers marking the precise moment when multiple spacecraft will achieve optimal viewing geometry for 3I at LS. It's 4:30 a.m. Eastern Time on October 28, 2025, and the greatest coordinated observation campaign in astronomical history is about to reach its climax. Across the globe, from Hawaii to Chile to the Canary Islands, hundreds of astronomers are preparing their instruments for what many consider the observational opportunity of a lifetime. The Hubble Space Telescope, humanity's most famous orbital observatory, has been tracking 3I at LS for months with the patience of a cosmic photographer waiting for the perfect shot. From its vantage point, 340 miles above Earth's atmosphere, Hubble's 2.4-meter mirror can resolve details in the comet's nucleus and inner coma that ground-based telescopes can only dream of achieving. The advanced camera for surveys has been capturing images in multiple wavelengths, building a time-lapse sequence that shows the comet's evolution as it approaches perihelion with unprecedented clarity. But Hubble's optical views, spectacular as they are, represent just one instrument in an orchestra of observation. The James Webb Space Telescope, positioned at the L2 Lagrange point nearly 1 million miles from Earth, brings infrared capabilities that can peer through the dust clouds surrounding 3I at LS to examine the comet's nucleus directly. Webb's 6.5-meter segmented mirror collects 25 times more light than Hubble, and its infrared instruments can detect the thermal emission from ice grains and organic molecules that remain completely invisible to optical telescopes. The coordination required for this multi-spacecraft observation campaign defies imagination. Each telescope and space probe operates on carefully planned schedules that must account for orbital mechanics, solar interference, and the competing demands of other scientific observations. The timing windows for optimal observations of 3I at LS are measured in hours, not days, and missing these windows means waiting years for similar opportunities with other interstellar objects. Parker Solar Probe, NASA's mission to touch the Sun, finds itself in a unique position to contribute to the 3I@LS campaign. Launched in 2018 to study the solar wind and corona up close, Parker's highly elliptical orbit brings it closer to the Sun than any previous spacecraft. During 3I@LS's perihelion passage, Parker will be positioned to measure the solar wind conditions that the comet encounters, providing crucial data about the environment that drives the explosive gas production Chen's team detected. The Parker Solar Probe data streams are unlike anything else in space science. The spacecraft encounters temperatures exceeding 2,500 degrees Fahrenheit and solar wind velocities that would strip away any unprotected spacecraft in minutes. Its heat shield, made of carbon composite material 12 centimeters thick, must withstand thermal stresses that would vaporize most materials instantly. Yet from behind this protection, Parker's instruments can measure the magnetic field strength, particle densities, and electromagnetic conditions that 3I@LS experiences as it races through the inner solar system. Dr. Elena Vasquez, the mission scientist responsible for coordinating Parker's observations, describes the challenge. We're trying to measure the solar wind properties along the exact trajectory that 3I@LS will follow, but we're doing it from a spacecraft that's also moving at incredible speed through a constantly changing environment. It's like trying to measure wind conditions for a race car while you're also racing around the same track in another car. The European Space Agency's contribution to the observation campaign centers on two spacecraft orbiting Mars, Mars Express and the Trace Gas Orbiter. These missions, originally designed to study Martian atmosphere and geology, have been repurposed to observe 3I@LS during its closest approach to the Sun. Their position beyond Earth's orbit provides a different perspective on the comet's tail structure, and allows observations during periods when solar conjunction blocks the view from Earth. Mars Express, launched in 2003 and still operational after more than 2 decades in space, carries the high-resolution stereo camera and various spectrometers that can analyze the composition of 3I@LS's atmosphere. The spacecraft's highly elliptical orbit around Mars provides observation windows lasting several hours during each 12-hour orbital period, allowing detailed monitoring of changes in the comet's activity as it approaches and recedes from perihelion. The Trace Gas Orbiter, a more recent addition to the Mars exploration fleet, brings modern instrument capabilities that complement Mars Express's aging but still functional sensors. Its ultraviolet and visible spectrometer can detect trace gases in the comet's atmosphere at concentrations measured in parts per billion, while its thermal infrared mapping spectrometer can measure temperature variations across the comet's nucleus with precision sufficient to identify individual active regions. But the real drama of the observation campaign unfolds in the control rooms, where human operators must make split-second decisions based on rapidly changing conditions. Sarah Kim, the lead coordinator for ground-based observations at the European Southern Observatory, hasn't slept more than 4 hours in any of the past 7 days. Her responsibility is to orchestrate observations from 8 different telescopes across 3 continents, timing each observation to maximize scientific return while accounting for weather, equipment failures, and the dozens of other variables that can derail astronomical observations. The stress is incredible, Kim explains during a brief break between observation sequences. We've been planning this campaign for 2 years, but you can't plan for everything. Last night, clouds rolled in over Perihelion, just as we were beginning a crucial spectroscopic sequence. We had 47 minutes of clear sky at La Palma to grab the same data, but that meant completely reconfiguring our observation schedule in real time. The data packets streaming back from these various observatories represent a technological marvel in their own right. High-resolution spectra from ground-based telescopes generate gigabytes of data per hour. Space-based observations add additional data streams that must be relayed through NASA's Deep Space Network and ESA's ground stations around the world. The total data volume from the 3I@LS campaign will exceed several terabytes, requiring specialized storage and processing facilities to handle the analysis. At the Atacama Large Millimeter Array in Chile, the world's most sensitive radio telescope array, operators are pushing their instruments to the very limits of sensitivity in an attempt to detect complex organic molecules in 3I@LS's tail. ALMA's 54 12-meter antennas work together as a single telescope with an effective diameter of up to 16 kilometers, providing resolution sharp enough to distinguish details in the comet's atmosphere that would be invisible to any other instrument. The radio observations require extraordinary precision because the molecules they're trying to detect emit signals that are billions of times weaker than typical radio sources. Dr. James Morrison, ALMA's project scientist for the 3I at LS campaign, describes the challenge. We're looking for spectral lines that are barely above the noise level, from molecules that exist in concentrations of parts per trillion, in an object that's moving at 130,000 miles per hour. It's like trying to tune in a radio station that's broadcasting from the moon while you're driving down a highway during a thunderstorm. The international cooperation required for this observation campaign extends far beyond just sharing telescope time. Data analysis algorithms developed at MIT are being used to process spectra obtained by Japanese telescopes. Software written by European programmers is controlling instruments built by American companies and operated by Chilean technicians. The scientific questions being addressed by 3I at LS require expertise in planetary science, stellar evolution, astrochemistry, and orbital mechanics, fields that no single institution could cover comprehensively. Yet despite this unprecedented level of international cooperation, technical challenges continue to threaten the success of the campaign. Solar conjunction, the period when 3I at LS passes nearly behind the Sun as viewed from Earth, will block radio communications with several spacecraft for crucial days during the comet's most active period. Ground-based telescopes must contend with the comet's proximity to the Sun in the sky, which limits observation windows to brief periods before dawn or after sunset, when the comet is visible, but the sky is still dark enough for sensitive measurements. The real-time decision-making required during these critical observation periods pushes both human operators and automated systems to their limits. When the Spitzer Space Telescope detected an unexpected brightening in 3I at LAVS's infrared emission on October 26, mission controllers had less than 6 hours to reprogram observation sequences for multiple other telescopes to follow up on the discovery. The coordination required phone calls between control centers in California, Hawaii, Chile, and Spain, all while the comet continued its relentless approach toward the Sun. Perhaps most remarkably, amateur astronomers around the world are also contributing to the observation campaign. While their equipment cannot match the sensitivity of professional observatories, their geographic distribution and flexible schedules allow them to provide continuous monitoring that fills gaps in professional coverage. The Global Amateur Astronomy Network has mobilized hundreds of observers who are tracking 3I at LETH's brightness variations, tail structure, and overall morphology with dedication that would put many professionals to shame. The psychological pressure on the professional astronomers leading this campaign is intense. Many have invested years of their careers in developing the techniques and instruments needed to study interstellar objects like 3I at LS. The failure of a crucial observation due to equipment malfunction or human error could set back their research programs by decades. Yet the potential scientific rewards are equally extraordinary. The data being collected during these crucial weeks will provide insights into stellar formation, planetary system evolution, and interstellar chemistry that could revolutionize our understanding of the galaxy. In the Parker Solar Probe Mission Control Room, alarms suddenly begin sounding as the spacecraft's high-gain antenna loses lock with Earth. The data stream that has been providing real-time measurements of solar wind conditions goes silent just as 3I at LS reaches its point of closest approach to the Sun. Controllers work frantically to re-establish contact, knowing that they may be missing the most important measurements of the entire mission. The silence stretches for 17 agonizing minutes before the telemetry signal returns, bringing with it data that will soon reveal the most shocking discovery yet about this visitor from another star. The global network of observers waits in collective tension, their instruments pointed toward a tiny moving point of light that carries within it secrets from the depths of space and time. What they're about to discover will challenge everything they thought they knew about the cosmos. 3 days after Perihelion, as 3I at LS began its journey back toward the outer solar system, Dr. Michael Zhang was staring at his computer screen in complete bewilderment. The post-processing algorithms had just finished analyzing 17 hours of continuous observations from the Very Large Telescope Array, and the results made no sense. The dust grain size distribution in the comet's tail was unlike anything ever recorded. Instead of the typical range of particles from microscopic specks to pebble-sized chunks, 3I at LS was producing dust grains with properties that seemed to violate basic principles of cometary physics. The spectral analysis showed mineral compositions that shouldn't exist in any object formed within our solar system. The dust analysis represents one of the most sophisticated techniques in modern astronomy. As sunlight scatters off dust particles in the comet's tail, the wavelength-dependent scattering patterns reveal information about particle size, shape, and composition with remarkable precision. Different minerals scatter light in characteristic ways. Silicate grains create broad absorption features in infrared wavelengths, while metallic particles produce distinctive polarization signatures. By analyzing these scattering patterns across the entire electromagnetic spectrum, astronomers can essentially perform a chemical analysis of dust grains millions of miles away. What Zhang's team discovered was unprecedented. The dust from 3I at LS contained mineral phases that form only under conditions of extreme pressure and temperature, conditions that exist in the interiors of large asteroids or planets, not in the cold outer reaches of stellar systems where comets typically form. Olivine and pyroxene crystals showed crystal structures indicating formation at pressures exceeding 50,000 atmospheres and temperatures above 1,500 degrees Celsius. These weren't the fluffy aggregates of interstellar dust that theoretical models predict for comet formation. These were fragments of processed, differentiated material. The implications were staggering. If 3I at LS contained fragments of differentiated material, it suggested that the comet had formed from the debris of destroyed planets or large asteroids. The stellar system where it originated must have undergone catastrophic collisional evolution, grinding planets into fragments that were later incorporated into the icy bodies that became interstellar comets. It was evidence of planetary destruction on a scale that challenged existing models of how stellar systems evolve, but the dust grain analysis was just the beginning of the post-perihelion surprises. Careful timing measurements of brightness variations revealed that something fundamental had changed in the comet's rotation. 3I at LS had been spinning with a period of 7.3 hours when first discovered, a typical rotation rate for a comet-sized object. But after perihelion, the rotation period had decreased to 6.8 hours, a change that represented a 7% increase in rotation rate. This wasn't the gradual spin-up that sometimes occurs as gas jets create torques on a comet's surface. This was a sudden dramatic change that could only be explained by a significant alteration in the comet's internal structure. The most likely explanation was fragmentation. Internal stresses caused by extreme solar heating had caused portions of the comet's nucleus to break away, reducing the moment of inertia and causing the remaining core to spin faster, like a figure skater pulling in their arms. Dr. Lisa Patterson, who led the rotation analysis team at MIT, described the implications. We're not just looking at surface changes here. The magnitude of the spin-up suggests that 3I at LS lost a substantial fraction of its mass during perihelion passage. We're talking about chunks weighing hundreds of thousands of tons being expelled from the nucleus. It's like watching a mountain explode in slow motion. The fragmentation hypothesis was supported by high-resolution imaging from the Hubble Space Telescope, which detected what appeared to be secondary condensations in the comet's inner coma. These condensations, visible as bright knots of material distinct from the primary nucleus, were consistent with fragments of the original nucleus that had been blasted away by internal pressure from rapidly sublimating ice. The fragments were too small and too embedded in the comet's dusty atmosphere to be resolved individually, but their collective light signature was unmistakable. Time-lapse sequences from multiple ground-based observatories showed these secondary condensations evolving over days and weeks following perihelion. Some appeared to be breaking up further, creating cascading fragmentation events that filled the comet's inner atmosphere with debris. Others seemed to be developing their own independent tails, as their icy surfaces began sublimating under continued solar heating. It was a spectacular display of cosmic destruction captured in real time by humanity's most advanced astronomical instruments. The fragmentation process also provided an unprecedented opportunity to study the comet's internal composition. Material that had been buried deep within the nucleus, protected from cosmic ray bombardment and thermal processing during millions of years of interstellar travel, was suddenly exposed to solar radiation and became accessible to spectroscopic analysis. It was like archaeological excavation on a cosmic scale, revealing layers of material that recorded the conditions present when 3I at LS first formed around another star. The spectroscopic analysis of the newly exposed material revealed the most shocking discovery yet: complex organic molecules with isotopic signatures that could only be explained by formation in pre-solar environments. These weren't the simple organic compounds typically found in solar system comets. These were polycyclic aromatic hydrocarbons, amino acid precursors, and even what appeared to be fragments of more complex biological molecules, all with carbon, nitrogen, and oxygen isotope ratios that indicated formation before our Sun existed. Amanda Foster, the astrochemistry specialist analyzing these organic signatures, could barely contain her excitement. We're looking at chemistry that's older than our solar system. These molecules formed in the interstellar medium, possibly in the stellar wind of red giant stars, or in the shockwaves created by supernova explosions. They've been preserved in this comet for over 7 billion years, carried across the galaxy like a time capsule from the early universe. The age determination came from careful analysis of the isotopic ratios in the organic molecules. During stellar nucleosynthesis, different generations of stars produce slightly different ratios of isotopes like carbon-12 to carbon-13 and nitrogen-14 to nitrogen-15. By comparing the isotopic signatures in 3I, Atlas's organic compounds with models of galactic chemical evolution, Foster's team could estimate when and where in the galaxy these molecules had formed. The results suggested an age of 7.2 billion years, plus or minus 400 million years. This made the organic compounds in 3I at LS significantly older than our solar system, which formed 4.6 billion years ago. It also indicated formation in a region of the galaxy where stellar evolution had proceeded differently than in our local stellar neighborhood, producing isotopic signatures that reflected different stellar populations and metallicity gradients. The preservation of these ancient organic compounds through billions of years of interstellar travel required conditions that challenged existing models of interstellar chemistry. Cosmic ray bombardment should have destroyed complex organic molecules over such timescales, unless they were protected by thick layers of ice or incorporated into grain structures that provided radiation shielding. The fact that these molecules survived suggested that 3I at LS had spent most of its interstellar journey in a relatively protected environment, possibly within a dense molecular cloud that provided additional shielding from cosmic rays. The detection of these pre-solar organic compounds also had profound implications for astrobiology. If complex organic chemistry could survive for billions of years in interstellar environments, it suggested that the building blocks of life might be distributed throughout the galaxy much more efficiently than previously thought. Interstellar comets like 3I at LS could serve as delivery vehicles for advanced organic chemistry, seeding young planetary systems with the molecular precursors necessary for life to emerge. The amino acid precursors detected in the comet's newly exposed material were particularly intriguing. Glycine, the simplest amino acid, showed clear spectroscopic signatures in multiple independent observations. More complex amino acids like alanine and serine were present at lower concentrations but were still detectable with the most sensitive spectrographic techniques. The chirality of these molecules, their handedness, couldn't be determined from astronomical observations, but their mere presence in an interstellar object was revolutionary. The discovery process itself revealed the power of modern astronomical techniques. The organic molecules were detected through their characteristic vibrational signatures in infrared spectra, patterns of absorption and emission that are as unique as fingerprints. But these signals were incredibly weak, requiring integration times of many hours and sophisticated noise reduction algorithms to extract them from the overwhelming background of thermal emission from dust grains and ice particles. The data processing pipeline that made these discoveries possible represents a marvel of 21st century computational astronomy. Raw spectra from ground-based and space-based telescopes are processed through algorithms that can identify and classify thousands of spectral lines simultaneously, comparing them against databases containing the signatures of millions of known and predicted molecular species. Machine learning techniques trained on laboratory spectra help identify the signatures of molecules that have never been detected in space before. Yet, for all the technological sophistication involved in these discoveries, the interpretation of the results required old-fashioned scientific detective work. Each new spectroscopic signature had to be confirmed through multiple independent observations. Alternative explanations for unusual isotopic ratios had to be carefully considered and ruled out. The possibility of contamination from terrestrial sources had to be rigorously excluded through comparison with blank sky observations and instrument calibration data. The convergence of evidence from multiple independent lines of investigation painted a picture of 3I at LS that was far more complex and ancient than anyone had anticipated. The unusual dust grain composition, the dramatic fragmentation during perihelion passage, and the detection of pre-solar organic compounds all pointed to the same conclusion. This wasn't just any interstellar comet. This was a relic from the early galaxy, a survivor from an era when stellar systems formed under conditions very different from those that gave birth to our sun and planets. The rotation changes and fragmentation events also provided crucial data about the comet's internal structure and composition. The way the nucleus responded to thermal stress revealed information about its mechanical properties, internal density distribution, and the strength of the materials that held it together. These properties in turn provided clues about the conditions under which 3I at LS had formed, and the environments it had encountered during its billions of years of interstellar travel. As the post-perihelion analysis continued, each new discovery added another piece to the puzzle of understanding not just 3I at LS itself, but the broader population of interstellar objects that must be wandering through our galaxy. The comet was revealing itself to be a Rosetta Stone for deciphering the chemistry and physics of stellar system formation in the early universe, carrying within its ancient ices the preserved record of cosmic processes that had shaped a galaxy billions of years before Earth existed. But even as astronomers worked to understand these remarkable discoveries, new observations were revealing that the story of 3I at LS was far from over. The comet's trajectory after perihelion would carry it through environments that might trigger additional changes and revelations, potentially providing even more insights into the cosmic processes that had created this remarkable visitor from the stars. As December's chill settles over Earth, 3I at LS emerges from behind the sun like a phoenix reborn from cosmic fire. The comet that disappeared into solar conjunction 6 weeks ago bears little resemblance to the object that first caught astronomers' attention in January 2025. Its nucleus, stripped and sculpted by the solar furnace, now displays activity patterns that will puzzle scientists for decades. Its tail, once a simple stream of gas and dust, has evolved into a complex structure showing multiple ion streams and dust clouds that tell the story of its violent encounter with our star. But perhaps most remarkably, its trajectory now carries it toward an encounter with Jupiter that will provide one final opportunity to unlock the secrets of this ancient wanderer. The reappearance observations began on December 3, 2025, when the Atacama Large Millimeter Array detected the first faint radio signals from 3I at LS as it emerged from the sun's glare. The comet was still 1.8 AU from Earth, but ELMA's extraordinary sensitivity allowed detection of carbon monoxide emission lines that revealed ongoing activity. Despite the comet's increasing distance from the sun, this continued activity, months after perihelion, was further evidence that 3I at LS operated by rules fundamentally different from ordinary comets. Dr. Yuki Tanaka, leading the post-conjunction observation campaign from ELMA's control room, described the moment of rediscovery. We'd been searching for weeks, scanning the predicted position with growing anxiety. Then at 1432 UT, there it was, a spectral line at 115.3 GHz that could only be carbon monoxide from 3I at LS. After 6 weeks of silence, our interstellar visitor was talking to us again. The December observations revealed a comet transformed. High-resolution imaging from the restored Hubble Space Telescope showed that the nucleus had developed a distinctly non-spherical shape, likely the result of uneven mass loss during perihelion passage. Spectroscopic analysis indicated that the composition of gases being produced had changed dramatically, with water vapor now dominating over carbon dioxide for the first time since the comet's discovery. This compositional shift suggested that the perihelion passage had stripped away the outer layers enriched in volatile CO₂-driven, but the most significant development was the comet's upcoming encounter with Jupiter. Orbital calculations showed that 3I at LS's post-perihelion trajectory would carry it within 0.15 AU of Jupiter in March 2026. Close enough for the giant planet's gravitational field to significantly alter the comet's path. This encounter presented an unprecedented opportunity to study how an interstellar object responds to gravitational perturbation by a major planet, and potentially to gain new insights into the comet's internal structure through careful monitoring of how Jupiter's tides affect its activity. The Jupiter encounter also carried profound implications for the comet's ultimate fate. Preliminary calculations suggested that the gravitational assist from Jupiter would accelerate 3I at LS to even higher velocities, potentially reaching speeds of 150,000 miles per hour as it departed the solar system. This acceleration would reduce the time needed for the comet to reach interstellar space from decades to just a few years, but it would also make the comet increasingly difficult to observe as it rapidly receded from the Sun. Catherine Reynolds, the orbital dynamics specialist calculating 3I/Laus's future trajectory, explained the complexity of the prediction. Jupiter's gravity doesn't just change the comet's speed and direction, it also creates tidal forces that can trigger new episodes of activity, potentially causing additional fragmentation or altering the comet's rotation in unpredictable ways. We're trying to model the interaction between a 300 Earth-mass planet and a fragmented, actively outgassing comet nucleus. It's like predicting the path of a spinning football through a hurricane. The scientific legacy of 3I/LS was already becoming clear even before its final departure. The comet had provided the first detailed spectroscopic analysis of an interstellar object, revealing composition and activity patterns that challenged fundamental assumptions about cometary physics. The detection of pre-solar organic compounds had opened new avenues for understanding the distribution of complex chemistry throughout the galaxy. The unusual dust grain properties had provided insights into planetary formation and destruction processes in other stellar systems. Perhaps most importantly, 3I/LS had demonstrated that interstellar objects are not the rare curiosities they were once thought to be. The detailed observations of this single comet had revealed such complexity and diversity that astronomers now estimated there could be millions of similar objects passing through our solar system every year, most too faint or too distant from the Sun to be detected with current technology. The universe was beginning to reveal itself as far more interconnected than previously imagined, with organic chemistry and planetary debris flowing between stellar systems in a vast galactic recycling process. The technological advances driven by the 3I/LS observation campaign were themselves transformative. New spectrographic techniques developed to analyze the comet's unusual composition were already being applied to studies of exoplanet atmospheres and protoplanetary disks. Machine learning algorithms trained to identify organic molecules in cometary spectra were finding applications in the search for biosignatures in the atmospheres of potentially habitable worlds. The international cooperation frameworks established for coordinating observations were becoming models for future multi-messenger astronomy campaigns. Dr. Elena Rodriguez, reflecting on the 2-year observation campaign, captured the transformative nature of the discovery. 3I/LS didn't just teach us about interstellar comets, it taught us about the galaxy itself. Every spectral line, every brightness variation, every grain of dust in its tail, carried information about stellar formation, planetary evolution, and the cosmic processes that connect all stellar systems. We started by studying one comet, but we ended up studying the entire galaxy. The educational impact of 3I/LS extended far beyond the professional astronomical community. The comet's dramatic perihelion passage, captured in stunning images and time-lapse sequences, had inspired a new generation of students to pursue careers in astronomy and space science. Planetarium shows featuring 3I/LS had attracted record audiences worldwide. Social media platforms had buzzed with amateur observations and citizen science contributions that had genuinely enhanced the professional observation campaign. The comet's story also resonated deeply with the human fascination with exploration and discovery. Here was an object that had traveled for millions of years across the galaxy, carrying within it the chemical fingerprints of stellar environments humanity might never visit directly. Its brief passage through our solar system provided a tantalizing glimpse of the vast cosmos beyond our local stellar neighborhood, a reminder that Earth exists within a galaxy teeming with worlds, chemistry, and processes that we are only beginning to understand. As 3I/LS continued its journey toward the Jupiter encounter and eventual departure from our solar system, the Large Synoptic Survey Telescope, scheduled to begin operations in 2026, would have the sensitivity to detect interstellar objects much earlier and at greater distances than previous surveys. The James Webb Space Telescope was developing new observation protocols, optimized for rapid response studies of newly discovered interstellar objects. The search for the next 3I/LS was being driven by more than scientific curiosity. The discoveries made during the 2025 observation campaign had demonstrated that interstellar objects carry information about galactic processes that cannot be obtained through any other means. They are the only samples of other stellar systems that come to us naturally, without requiring the enormous technological investments needed for interstellar space missions. Early detection networks were being established to provide weeks or months of advance warning for future interstellar visitors. These networks combined automated sky surveys with artificial intelligence systems trained to recognize the unusual orbital signatures and spectroscopic properties that distinguish interstellar objects from solar system residents. The goal was to begin detailed observations of the next 3I at LS from the moment it entered the outer solar system, potentially years before its closest approach to the Sun. The legacy of 3I at LS was also reshaping theoretical models of galactic evolution and stellar system formation. The comet's age, estimated at over 7 billion years, suggested that it had formed during an era when the galaxy was much younger and stellar formation was proceeding under different conditions than exist today. Its unusual composition provided constraints on models of how the interstellar medium has evolved over cosmic time, helping astronomers understand how successive generations of stars have enriched the galaxy with heavy elements. The detection of complex organic molecules in 3I at LS had particularly profound implications for astrobiology. If such molecules could survive for billions of years in interstellar environments and be delivered to planetary systems throughout the galaxy, it suggested that the chemical building blocks for life might be far more widely distributed than previously thought. The comet had effectively demonstrated that the galaxy itself might serve as a vast chemistry laboratory, synthesizing and distributing complex molecules that could serve as the foundation for biological evolution wherever suitable planetary environments exist. As March 2026 approached, and the Jupiter encounter drew near, the astronomical community was preparing for what might be the final act in the 3I at LS story. The gravitational perturbation from Jupiter would not only accelerate the comet toward its final departure, but might also trigger new episodes of activity that could reveal additional secrets about its internal structure and composition. Some models predicted that Jupiter's tidal forces could cause complete disruption of the already fragmented nucleus, creating a spectacular display of cosmic destruction that would be visible from Earth for months. Yet even as 3I at LS prepared for its final performance, astronomers were beginning to detect hints of its replacement. Deep sky surveys were revealing several objects with unusual orbital characteristics that might represent the next generation of interstellar visitors. Comet K-Cells 2026 Q2, discovered in early 2026, showed spectroscopic properties similar to 3I at LS and appeared to be following a hyperbolic trajectory that suggested extrasolar origins. The anticipation surrounding these new discoveries reflected how profoundly 3I at LS had changed astronomy's perspective on interstellar objects. What had once been regarded as rare curiosities were now understood to be regular visitors carrying crucial information about galactic processes and stellar system evolution. Each new interstellar object represented an opportunity to expand humanity's understanding of the cosmos and our place within it. Standing beneath the night sky in the early months of 2026, watching the faint glow of 3I at LS as it approached its final encounter with Jupiter, observers could reflect on the remarkable journey of discovery that began with a single anomalous detection in January 2025. This ancient wanderer from another star had carried within its icy depths the secrets of cosmic processes that shaped the galaxy billions of years before Earth existed. Its brief visit to our solar system had provided humanity with insights into stellar formation, planetary evolution, and the distribution of complex chemistry throughout the universe. But perhaps most importantly, 3I at LS had demonstrated that we live in a universe far more interconnected and dynamic than previous generations could have imagined. The galaxy is not a collection of isolated stellar systems, but a vast, integrated ecosystem where matter, energy, and even complex chemistry flow between stars in processes that operate on timescales of millions and billions of years. We are not alone in space, separated from other worlds by impossible distances, but participants in galactic processes that connect us to stellar systems throughout the Milky Way. As 3I at LS disappears forever into the cosmic deep, accelerated by Jupiter toward velocities that will carry it beyond the reach of our telescopes and into the interstellar night, it leaves behind a transformed understanding of our place in the cosmos. We are cosmic citizens, residents of a galaxy teeming with worlds and chemistry and processes that we are only beginning to explore. The next interstellar visitor may already be on its way, carrying new secrets from the depths of space and time, ready to reveal new chapters in the ongoing story of cosmic exploration and discovery. The universe is vast, ancient and full of wonders waiting to be discovered. 3I at LS was just the beginning.